Okay, problem 13 says that an irreversible reaction has one reactant and one product. So it's A goes to P, and it's irreversible. There's no back reaction. And it has a rate law that's 3/2 order in the reactant. In other words, we have a rate law that says that we have some rate constant times the reactant to the 3/2 power. That's what it means to say that it's 3/2 order. And then it asks that we find the integrated rate equation for the A goes to P reaction for both A and for P. So we're going to find how A and P vary versus time. And then we want to, the problem says to plot how those things look as a function of time. And the purpose of the plot, of course, is just to give us a feeling for how this thing looks in this odd case. So this problem is asking us to basically exercise our ability to find integrated rate equations and figure out how integrated rate equations come about in the first place. So to do that, we need to write a rate equation to begin with. So this is problem 14 over here. No, sorry, 13 over here. And the rate equation is going to be minus dA dt is equal to k times A to the 3/2 power, right, for a 3/2 order reaction. And now in order to, what finding the integrated rate equation means is solving this differential equation. So separating the variables on both sides, we have minus dA over A to the 3/2 power is equal to k times dt. Integrating both sides, so from A0 up to A, dA over A to the 3/2 power minus is equal to the integral from 0 to t of k dt. And now doing those integrals, this gives us, well, let me say this can be rewritten as the integral. Well, let me just do it. Let me not kind of do it off to the side. Let me do it a little bit more properly. That's minus the integral from A0 up to A of A to the minus 3/2 power times dA. And that's equal, I can do this integral over here now, k times t. This integral is a power law integral. That gives us minus 1 over minus 1/2 times A to the minus 1/2 power evaluated from A0 up to A, and that has to equal kt. That is equal to, the minus signs cancel, a 2 times A to the 1/2 power, that's putting in this upper limit, minus putting in the lower limit, A0 to the minus 1/2 power, sorry. And that's equal to kt. And that can be considered to be an integrated rate law in its own right. This is sort of the equivalent, for example, of log of A is equal to log of A0 plus kt, or minus kt, for a first order reaction, or 1 over A is equal to 1 over A0 plus kt for a second order reaction. This is the equivalent kind of thing for this 3/2 order, but it's useful sometimes to actually solve all the way out for A as a function of time. In fact, we're going to need to do that in order to get P later. So let's do that. We have then that A to the minus 1/2 power equals A0 to the minus 1/2 power plus kt over 2, doing a little bit of solving. And now, taking the inverse of both sides, I have A to the plus 1/2 power is equal to 1 over A0 to the minus 1/2 power plus kt over 2. And now squaring both sides, I get that A is equal to 1 over A0 to the 1/2 power plus KT over 2, and all of that squared. Let's just test to see if we get something reasonable from that. So first put a box around it. And one way to do that is to set time equal to 0 here. If we set time equal to 0, we better get A0 out, right? So if we set that equal to 0, then we have 1 over A0 to the 1/2 power squared. That's A0 to the 1/2 power squared, which is just A0. So we do get the initial concentration out when time is equal to 0, and at least we passed that much test. In fact, that answer is right. And you can also, when you're doing these kinds of problems, you can also test whether this answer is right, because you can just take the time derivative of A and see whether you satisfy the differential equation, right? If I take the time derivative of A, I have to get out the following. And I won't do that here because it takes a bunch of time and it's a bunch of algebra, but you can be sure that this answer is right by just taking the time derivative and seeing if you get back your differential equation. All right, so we now have our integrated rate equation for A. It also asks us to find the way that P depends on time. And to get that, we're going to use the fact that the concentration of A plus the concentration of P has to be a constant, right? Since it's A goes to P, we can't lose anything net, right? Whatever gets destroyed on the A side has to show up on the P side, so the total of both of those has to stay constant with time. At time 0, we have A0 plus P0 is equal to the same constant. We assume that there is no P to begin with, there's no product to begin with, and therefore the constant is just equal to A0, and so we have that A plus P is equal to A0, and that means that P is equal to A0 minus A, and we have A up here. And so finally we have that P is equal to A0 minus all this stuff up here. So 1 over A0 to the 1/2 power plus KT over 2 squared. And that's P. So now we've answered both parts of the original question for part A. The next part is just to plot the results that we get as a function of time, and I did that earlier for the key. Can't do that here in the video very well, so let's just look and see what I got earlier down here. There it is. Yes, there it is. So first of all, here's the answer we just got for how A varies with time and for how P varies with time. I've reworked it a little bit to make it a little bit nicer for plotting purposes, but all right, it's basically the same answers. In fact, here's the answer we just got for P. Here's the answer we just got for A, in the same exact form as they were over in our derivation just a minute ago. And here are the plots, and there's not too much to say about it except that, yes, the A concentration goes down, the P concentration goes up. And once again, you can't tell really what the order of reaction is qualitatively by looking at these plots by eye, because you can't tell really by eye whether that's an exponential decay here or whether it's some other kind of decay. Can't tell first order from second order, can't tell either of them from 3/2 order, can't tell them from 1/2 order, can't tell them from any other order just by eye. And so the way to tell is by generating a linear plot. And let's go over here and see what that would be in this case. To do that, let's go back up here, right? We have this relationship this isn't quite as convenient if what you want to do is calculate a as a function of time, but it's more convenient if you want to see what kind of plot should give you a straight line. And so here, going one step more in derivation, we have that a to the minus 1/2 power is equal to a 0 to the minus 1/2 power plus kt over 2, right? And now if I say that this is y, and if I say that t is x, then this would be mx here, and then that would have to be b here. And so if I plot 1 over the square root of a versus time, I should get a straight line. I should get, if I plot 1 over the square root of a here versus time, I should get a straight line. And the slope of that straight line should be k over 2. And the intercept of that straight line should be 1 over the square root of a0. And I think that is everything for this problem.